computer. Right. Okay, well, we're very pleased to welcome Lou, who is going to talk about the Jones polynomial and quantum computing.
So it says here on this slide.
Yeah, I can read.
Yes, right. Okay, shall I start?
Yeah, by all means.
Good. All right, here we go. Um, uh, this has some background. I don't know if I listed all the papers that are really relevant, but some of them anyway, mostly by Sam and myself. And um, in this case, one um, kind of interesting paper that happened a little while back by Sam, myself, and a whole bunch of people who, some of whom are in Munich, and they are chemists and they do nuclear magnetic resonance spectroscopy, and which is a kind of quantum computing, and we got them to use our algorithm to calculate the Jones polynomial using that method, which was fun. And we were doing it with three-strand braids. We, I'll be telling you about how to generalize the three-strand algorithm that I'll tell you about to n strands, and we were intending to get back and have them work on this, but it never hasn't so far happened that they did more. NMR methods are limited to a very small number of qubits, and so the quantum computers that the world wants are probably not going to come out of NMR, but they really are quantum computing in the form that one would like to have. This was a poster from that situation. And now, let's start at the beginning. I want to remind you about the basics of quantum mechanics and then how quantum computing works, and then talk about representing things so that one could build a quantum computer to calculate the Jones polynomial. So this is a capsule summary. I'm hearing little bells ringing. I'm not sure whether that's
Uh,
your computers or mine. Um,
it's the people entering, I'm afraid.
oh, that's fine. Just as
Don't
long
worry
as,
about it. It's just a
yeah,
nice musical background.
yes, it is, right. Um, so I want to summarize quantum mechanics, and here it is on one page. Um, the state of a physical system corresponds to a unit vector in a complex vector space. In the original quantum mechanics, the kind produced by Schrodinger, um, the Hilbert space, the complex vector space, was the space of complex solutions to Schrodinger's equation, which is in the upper left here. And I am not in my summary going to explain to you what is the meaning of Schrodinger's equation. I'm going to talk about it in a different mode, but if we had more time, we could relate what I'm about to say back to Schrodinger's equation indeed. The vector space can be finite dimensional if the number of outcomes of an experiment that you're thinking about is finite. Um, and then what you do is you make a list of all the complete list of outcomes of the experiment that you have in mind, um, and make each one of them a unit vector or orthonormal basis for the vector space. So each element in the vector space, each basis element is one of the possible outcomes of an experiment. And then the state of the physical system is going to be a complex linear combination of them of unit length, which means it looks like a sum of zi times ei, where I'm down on 2 here in this nutshell, which can be thought of as a generalized probability distribution for having one of those events occur. and this is particular to quantum mechanics, those are complex numbers, but it is a kind of probability distribution because the probability of one of the events occurring is the absolute square of the coefficient. So you could imagine, for example, that you had a die uh, with its 6 faces, and 1 through 6 would be the basis elements of the vector space. And then instead of having the usual probability vector for your die, which would be probably 1/6 times each of them added up, and then here's how you measure. Measurement takes the vector to one of the basis elements, just like throwing the die onto the table takes the die from its possibility of any one of the faces to a single face up, with 1/6 probability if it's a fair die. But here, there's more information than just the probability in this vector. The absolute square of the coefficient is the probability, and the sum of them is equal to 1, and those are probabilities. That's the way it works. But the actual coefficients of the vector are complex numbers. And that means that it is possible in the course of time for one such vector to be added to another such vector to interfere with them. And as a result, this model includes the possibility of the interference of things. A measurement-free process is modeled by a unitary transformation applied to the state vector. A unitary transformation means, for our finite dimensional look at this, a matrix which is equal to its own conjugate transpose, and it is configured in that way so that it preserves the length of the vector. It preserves the sum of the absolute squares of the coefficients. So undergoing a transformation in time without measurement means that you get a new vector which is a mix-up of the coefficients of the old vector by this linear transformation. And it's quite possible that some modalities will increase, some modalities will decrease. And that is the model. What has been eliminated from this model, from the discussion in this model, is how this is related to physical quantities like the energy of a system. And that I won't be talking about. But if you're trying to measure, if you're trying to design an algorithm, then you can look for designing a unitary transformation whose probabilistic effects, that is, the statistics of the measurement in relation to that unitary transformation, do what you want it to do. And that's the abstract problem of designing a quantum algorithm. In order to make it actually work, the unitary transformations involved have to actually be modeled by a real quantum system. And there you need to have the linkage to energy and other physical apparatus, which is part of the Schrodinger's equation and other aspects. But quantum mechanics in the abstract is described by this simple summary, and we can keep thinking about this whenever we want to see whether we're building a quantum algorithm. Now, the simplest example of such a vector is called a qubit. There are two alternatives, 0 and 1. These might be spin up and spin down for an electron. And a measurement will take you to 0 with probability absolute a squared, and it'll take you to 1 with probability absolute b squared. Oh, by the way, the notation of a vertical slash, some information, and a caret is called a ket, and the notion is due to Dirac, who took a bracket and divided it in half and calls it a bra and a ket. The bra is the other one and is the dual vector, and I'll probably use it in a moment so you'll see how it works. In fact, I want to discuss a quantum algorithm that will do the following. I want to show you how we could design a quantum algorithm that would compute the trace of a unitary matrix. And I do this with malice aforethought because this is how I'm going to make a quantum algorithm to compute the Jones polynomial. I'm going to create a unitary matrix that corresponds to a representation of the braid group that is related to the Jones. And then I'm going to set it up so that the trace of U is the essential information that I need in order to actually get the Jones polynomial from the U. So our problem is, how would you find the trace of a unitary matrix? And the unitary matrix is supposed to be a physical process. Remember the nutshell? It's a physical process. That means it's a black box. You may know what this matrix is. Maybe you know that it's a very large matrix of a certain kind that you are implementing, but you do not know it anymore from this point of view, because it's the physical process that is embodied in the matrix. The matrix itself is now a black box, and you would like to find the sum of its diagonal entries. And here is the algorithm. We're going to take the matrix and now the matrix acts on a vector, a ket, of some dimension, phi. And I'm going to take one extra tensor line along which I could input a single qubit, which in this slide I've simply inputted as 0. And then along that single line, I can apply a 2x2 matrix, because remember, a single tensor line corresponds to a two-dimensional vector space. One single line is a two-dimensional vector space. And generally, I am thinking of some n-dimensional vector space over here on the other solid line. But the upper line is a two-dimensional vector space line. On H can act on that. H acts on a qubit. Then there's the unitary matrix that I have. And from the outside, I can do the following with this black box. I can either apply it or not apply it, depending on whether the input along this line to the little circle is 0 or 1. If it's 0, I will not apply U. It just means that the bottom line will be the identity. And if it's 1, U will be applied. So if a linear combination of 0 and 1 comes hurtling down the upper line, then it will affect the next transformation, which is the controlled U, by doing the identity on the 0 part and doing U on the 1 part. And then after that has been applied, I apply H again in the upper tensor line. And now I have the output. So up until that great big half moon, quarter moon, until you get to the quarter moon, this composition is a unitary transformation. The controlled U is unitary. The H tensor 1 is unitary. The composition of all three of them is unitary. So I have produced, by setting up the linear algebra, a certain unitary transformation, and then I measure. And I measured to find out whether, upon measurement, I get 0 in the upper tensor line. If I get a 1, I don't regard that as a success, that part of the measurement. I want to see what the coefficient of 0 is in the upper tensor line. I want to know the probability of 0. I misspoke myself when I said the coefficient of 0, because I never see that. I only measure that a 0 happened. And if a 0 happened, I write it down in my statistics, and I keep track of the statistics, the proportion of zeros. And I run this algorithm again and again and again with the given input. And then what you will find is that 0 will occur with probability. We'll see why in a moment. 1/2 plus the real part of the inner product of phi with U with phi divided by 2. And there I've used the bracket notation. Phi is the covector, the dual vector to phi. U is the matrix, and phi on the other side. So this picks out the phi entry of u. That is, if we were in the basis, it would be, excuse me, if phi were the ith element of the basis, then this would be the I entry of u. And I have just written it a little more generally than that. So this tells me that I have a quantum algorithm here. This entire setup is the quantum algorithm. And in order to get information out of it, I have to measure repeatedly to satisfy my desire for the statistics. And that's another matter. You need to analyze how much measurement, how many times do you need to do this to have the statistics be accurate enough? But I'm not going to worry you about the statistical side. This algorithm doesn't compute the trace. It just computes one element of the diagonal if I were to choose a basis element. And then I have to do it as many times as the size of the matrix for each basis element. I have to look at the statistics of the appearance of it for each basis element. I have to take each basis element as the input and run it through and get the statistics for each basis element, and then I can add them all up, and as you see, I will get the real part of the trace. And then I can modify this whole thing by tweaking one of the lines a little bit, and I can get the imaginary part of the trace, and then I will be able to get the whole trace. So that's a lot of work, it would seem, just to get the trace of a matrix. But in fact, it's not bad as quantum algorithms go. So let's actually look at the algebra of that so you see how this works. The H is called the Hadamard, and that's a little unitary matrix. You can see what it does. Um, it takes the 0 element to the sum of 0 and 1, and it takes the 1 element to the difference between 0 and 1. It won't be hard for you to write that down as a matrix, but I think I didn't. Or did I? In the previous slide, I did, yes. The H on the first basis element is the sum of the basis elements. H on the second basis element is their difference. It's divided by root 2. You can see easily that this is unitary. Its conjugate transposes itself and it squares to be equal to the identity. So that's the H matrix. Now, the entire algorithm is up to the controlled U, but no farther. The entire algorithm is apply controlled U to H tensor 1 applied to 0 and psi, the input. So we can actually write this out just for the sake of getting used to this sort of thing. So I'm going to do the controlled U to H tensor 1. Well, H tensor 1 applied to 0 gives me the linear combination of 0 and 1 over the square root of 2. And then I'm going to apply the controlled U. So in the 0 part, I applied the identity to psi, and in the 1 part, I applied the U to psi, and there it is. That's the application of the controlled U. Then I'm going to apply the Hadamard one more time, and that means that each of those zeros and ones gets mixed up as a 0 plus 1 when we apply it again. So that means that I'm going to apply the Hadamard to 0 and the Hadamard to 1. That's the complete unitary applied, and that means I get 0 plus 1 on the 0 and 0 minus 1 on the 1, and we collect terms, and we get 0 tensored with psi plus u psi, and 1 tensored with psi minus u psi. And then I'm going to look for the expectation of 0, which is going to be equal to the psi plus u psi times its ket. And that gives me the inner product of those. And you work that out, you see, and you get psi psi, which is 1, and you get psi u star u psi and you get psi u psi and psi u star psi and collect it up. But you see, you get psi u dagger psi and you get psi u psi, and that adds up to the real part. And so it's a simple calculation to see that indeed the expectation is what you want. And the imaginary part, if you want an imaginary part, is obtained by modifying the algorithm a little bit, changing the Hadamard to a slightly different transform. And and there you are. That's a quantum algorithm, and it will compute the trace of a matrix if it's unitary. Notice that I did need unitary. I would have to work harder to get the trace of an ordinary matrix. Yeah, the reason unitary made it possible was that I could take that unitary that I was working with and make it part of the process. So I'm using the black box to find out something about the black box in this case.
Lou,
By
sorry to
yes,
interrupt, but there was a question about what's CU in the next slide.
do you
The
let's stay
CU.
with this slide.
Well, the previous slide, there was a CU.
The CU is the controlled U. The controlled U, as I described it,
Mm-hmm.
is, I have no pointer when I'm using this slideshow,
Right.
is the little blob connected to the U, which is acting on a single tensor line tensored with whatever the U does.
Okay.
And it acts by, if the extra line is 0, it acts on by the identity, and if the extra line is 1, it acts by U. Is that clear? Take a look
Yeah,
at what
yeah,
happened.
sure. I mean, I don't know who asked, but I hope that's clear.
Right, right. Well, I'm answering. So you see here in the equational version, the controlled U applied to H tensor 1 is when the little extra tensor line gives a 0, doesn't do anything, leaves psi alone. And when the 1 is there, it does U. Does that answer the question?
Yeah, I fine.
Yes.
Good.
Or
Okay.
whoever it
Good.
was.
Good.
Uh,
Okay. So, as I was saying, what you do is you enfold this given unitary in a larger unitary transformation by making it into a controlled U and flanking it with these Hadamards, a bit of clever linear algebra. And a lot of the quantum algorithms use various nicely designed bits of unitary linear algebra compositions in order to achieve their aims. And in this case, you see that by doing this linear algebra, we achieve the aim of getting an expectation for the measurement to be part of the information that we wanted. Okay. Um, so, so we have also, you can note that if you had an eigenvalue, um, well, then psi u psi would be lambda. And so the Hadamard test allows you to determine the eigenvalue to any degree of accuracy. And that turns out to be important for other quantum algorithms, not the Jones one, the way we're setting it up, that you would like to determine the eigenvalues of a unitary transformation. And there is a more refined algorithm called phase estimation, uh, which is a generalization of this algorithm. So, so I've concentrated on giving you a detailed picture of at least one quantum algorithm this way, because this one is the one we're going to want to use when we talk about Jones. So we want to talk about quantum braiding. This is a nice illustration uh, from a Scientific American article, and it's scientifically inaccurate, but metaphorically rather nice. You see the braid, and those are supposed to be quantum vortices in some two-dimensional physics down there that are somehow being controlled by, I don't know, is that a human or our quantum state up there? It's a nice illustration. But I need to remind you about some Jones polynomial things. So this slide could remind you about Temperley-Lieb algebra in the diagrammatic mode and how we might think about it using Bras and Ketz if we wanted to. A line is, I'm writing it horizontally, as sometimes we like to do. So a line, a morphism, is just an identity. A turnaround, a cap or a cup, could be thought of as a bra or a ket. Has the same formal properties as a bra or a ket. And then the the bra ket is the inner product, is the loop, is the scalar. But the ket bra is the cup cap of the Temperley-Lieb algebra, as you see. And it's not necessary, it's not unitary, that's just for this slide. But we might also use tensor lines, as I have been using tensor lines, in which case I could take that cup cap and tensor it with an identity, or I could take the identity, tensor the cup cap, call those P and Q, and those are the usual diagrammatic or categorical or plain algebraic elements for Temperley-Lieb. And they have the property that if you square P, for example, up there I've squared the smaller p, you get a scalar times P. And if you take Q and then P and then Q, you will just get Q. And if you take P and Q and P, you'll get P. These are the Temperley-Lieb relations, which can be extended diagrammatically across any number of lines. And the little wiggle being pull-outable corresponds to the fact that if you were to write this, you would have an identity about the cup and the cap that caused them to collapse out. And you would need to have such an identity. In the case of matrices, you would need the matrices to work out right in order to do that. In the diagrams, they simply pull. That's a picture of Temperley-Lieb and how you might diagram it. But, of course, what we're most concerned with here is how would we make some unitary transformation involving Temperley-Lieb. So let's go back to Jones to understand what it is we need. And in general, when I'm working here, I do need to think about diagrammatic matrices, so I have a slide here for this. When I write a wiggle, I may translate it into diagrammatic matrices in the following way. I have an index for the ends, and I have an index where two things are joined, so that this represents an MAI joined with an M upper IB. Upper because there are upper indices on the cup and lower indices on the cap. And the NBA then, the matrix that is the composition, is, well, it's supposed to be the composition of two matrices. And that means you must sum on the internal index. And so therefore, in the diagrammatic for matrices, if you have a free index, you don't necessarily sum on it. But if you have an internal index like the I, then you sum on it. And I may write it as one block matrix after I have combined it that way. So a cap could be a matrix with indices AB, and a cup could be another matrix. We'll come back to that point. But this is a point I think I'm going to skip about this, about teleportation. We could talk about teleportation another time. Let's go over to the knot theory. Well, you're all familiar with this. The Reidemeister moves on the one hand, the fact that you can represent knots and links by braids, closures of braids, and we have the braid group, which I sometimes write as S sub I, and sometimes I write as sigma I, and you'll see that I'm a little schizophrenic about whether SI is the generator or the flip of it. And then there is the bracket model for the Jones polynomial, which goes like I've indicated here, that you think of it as a skein expansion if you want, and then it is expanding the crossing into a horizontal smoothing and a vertical smoothing, and this doesn't have to do with braids necessarily, and you can then go ahead and recursively compute the coefficients are determined in such a way that the bracket is invariant under the second and third Reidemeister moves, and framing can be compensated for without any problem. I forgot to mention on this slide that the value of the loop, a single loop next to something, is minus a squared minus a to the minus 2, and that the value of a loop all by itself is normalized to 1. That's bracket. But the relationship with braiding is very important, and let's look at that. You might not have thought about that recently. Here's the bracket equation. And if you applied bracket to a braid inside the calculation of some braid closure perhaps, then it expands into a little diagram like that, and another one which is an identity diagram. And the little diagram with the horizontal smoothing can be interpreted as the diagrammatic Temperley-Lieb generator, in this case U2. So I have, using that one on the left as the braid generator, sigma 2, between second and third line, it says that bracket sigma 2 is A times U2 plus A inverse times the identity. And that tells me, in fact, if I think about it a bit, that I have a representation of the Artin braid group into the n-fold Temperley-Lieb algebra, n-strand braids into n-strand Temperley-Lieb, by taking sigma I, not sigma n, excuse me, and to a un plus a inverse times the identity. And the UIs, the diagrammatic UIs, satisfy the Temperley-Lieb relations, and everything. So then, what about calculating the bracket, which we'll regard as what we mean by calculating the Jones polynomial? What about calculating the bracket from this point of view? Well, the answer is quite simple. What you do is you define the following trace on the Temperley-Lieb algebra. The trace of a given element in the Temperley-Lieb algebra, which is going to be a sum of products of simple generators, and I'm thinking of x as a simple generator. Trace of x is going to be equal to delta, the value of the loop, raised to the number of loops in the closure of x minus 1. This, of course, is the bracket definition. But the bracket definition, in fact, gives us a trace function on the Temperley-Lieb algebra in this fashion. So, for example, at n equals 3, with u1 that, u2 that, and u1 u2 and u2 u1 those, we see that the trace of u1, when you close it, it gives you 2 loops, so the trace is delta. And the trace of u2 is delta. And the trace of u1 u2 is 1, because when you close that character, you only get 1 loop. And remember, a single loop evaluates to 1. And the trace of u2 u1 is 1. These trace evaluations are all you need now to calculate the bracket, which is the composition. The bracket of the closure of the braid is equal to the composition of that trace with the representation of the braid. This coincides exactly, modulo some changes of variable, with von Jones's original definition of the Jones polynomial, where his trace function is defined combinatorially on the Temperley-Lieb algebra by counting certain standard products. But it turns out, remarkably, that counting that he does to get a trace on Temperley-Lieb is exactly the loop count in this diagrammatic. So we can understand then that one good way of looking for an algorithm to compute the Jones polynomial would be to create a situation in which this representation of the braid group is unitary. And then all we have to do is compute the traces of certain matrices involved. If we can get the matrix traces to satisfy on the Temperley-Lieb generators these nice formula. Trace UI is delta trace U2. And in general, trace of UI should be equal to the appropriate closure count. So that's the strategy. So we're looking at the now this is where my notation flipped. when I wrote this slide earlier, I had used the opposite entry for the braid generator. So I wrote A times the identity plus A inverse times UI. You won't mind, and I'll be consistent with this for the braid generators from now on. So we're looking at this, and we would like this to be unitary. We want matrix representation, so this is unitary. How can I obtain this? Well, look at it. Suppose that A is a unit complex number. Then A star is its inverse. So that means that and suppose that UI is a real symmetric matrix. Then UI star is UI. And then if you take rho of sigma I star, you will get A inverse I plus A UI. And that indeed is the inverse in this representation of the rho. So we can obtain a unitary representation of the Temperley-Lieb algebra by using, for the bracket A, a unit complex number, and getting the UI adjusted so that it satisfies the Temperley-Lieb relations and is real symmetric. So that's what we want to do. And I'm going to show you how to do this in the three-strand case, and then I will talk about how to generalize it. The three-strand case is not hard, you'll see, if you take the right point of view. So I'm going to rewrite into Temperley-Lieb algebra for a moment. I'm going to let EI be UI over delta, so EI squared is EI. And then we have EI plus or minus 1, EI is tau EI, where tau is delta to the minus 2. That's just changing the variable a little bit. And EI and EJ commute for absolute I minus j greater than 1, which we won't have to use in this first example. So now consider some elementary projectors. Let E be ket bra A and F be ket bra B, where A is, remember, just a label for some vector. And we have that the inner product of A with A is equal to the inner product of B with B is equal to 1. And I do not assume that the inner product of A with B is 0. They aren't necessarily perpendicular. They're projectors in two different directions. So we have E squared equals E and F squared equals F. And now this is an instance of picking up the Temperley-Lieb relation. Just directly from the projector property. Look at EFE. You get A, you get the ket A, then you get the ket bra A, you get the ket bra B, you get the ket bra A again, and in the middle you get the inner product of A with B and the inner product of B with A, the absolute square of the inner product of A with B, and times E. So there's tau. So tau is that product of inner products. And you can check that FEF has exactly the same coefficient. So this really is an instance of Temperley-Lieb. And in this case, we don't have anything but a U1 and a U2. We're in the three-strand case with these 2x2 matrices. We have a U1, we have a U2. We aren't worrying about any higher U's. And now let's suppose that the bra A is a little vector A comma B, and the ket A is its transpose. So then the ket bra E is A squared AB, AB, and B squared, this little projector matrix, A squared plus B squared equals 1. And I want to obtain a specific representation and play with it to see if I can make it work. So I let E1, the simpler one, be just the one from 1, 0. So the vector is 1, 0 in one case and AB in the other. And I have these two. And you can check, of course, that, that in this case, the tau is just A squared. So that's just doing the exercise I just did in the case of these two vectors. One of them is 1, 0, and the other is AB. So now we go back to Temperley-Lieb and we define ui to be delta ui. And then we see that a squared should be delta to the minus 2. And so then we will have Temperley-Lieb in our usual form. And now think about the matrix parameters. A little bit of algebra has to be done here. A squared plus b squared is 1. So delta to the minus 2 plus b squared equals 1. So b squared equals 1 minus delta to the minus 2. And we want b to be real. So I need to put an inequality on delta squared. And I won't worry you about the inequalities, but I do have to put some inequalities in order to make sure that things are real. And then I'm going to have a equal to e to the I theta in the middle of that slide. Sorry, too much text. In the middle of the slide. A is e to the I theta, which means d, which is minus a squared minus a to the minus 2, is minus 2 cosine 2 theta, right? Do your Eulerian arithmetic. So what you then find is that you get a ranges of angles in the unit circle in which everything works. Not the whole unit circle, due to the inequalities I have to satisfy. And I won't worry you about those angles. You could, if you wanted to think about it carefully, you could. So you get some angles along which it will be unitary, and in those things are going to be working for us. So here's what it looks like when we finally write it out as some matrices. The D is in the correct range. The A is a root of unity. The U1 is just very simple, D0, 0, 0. And the U2 is this one with those square roots in it. And these two satisfy the Temperley-Lieb algebra. And then what we have is exactly what we want. We can define the representation on the two braid generators for the 3x3, for the 3-strand braid group by the formula that I told you. And we have a representation of the braid group that's unitary. Now, what about the traces? Let's see. The trace of U1 is D. And that is correct. That's what we want. D is the loop value. And the trace of U2 added up is also D. That's good. That's what we wanted. And if you take U1 times U2, you'll see that you only preserve the first row and the second row goes to 0, and you get a 1 in the upper corner. So the trace of U1, U2 is 1. And the trace of U2, U1 is 1. So the U1 and the U2, they satisfy the correct values for having just the trace calculate the Jones polynomial for you. You don't have to count loops anymore. You can actually just take the trace of the Temperley-Lieb matrices that come out of the braid group representation. When you represent some big 3-stranded braid and multiply it all out in the Temperley-Lieb representation, you're going to get a coefficient of the identity, a coefficient of U1, a coefficient of U2, a coefficient of U1, U2, and a coefficient of U2, U1. And when you take the trace, you're going to get delta or 1 accordingly on those UIs, and then you will be landing on the bracket. So after a little fiddling, you end up with what I just said here. There's too much word in the slide, but it's what I just said. And down at the bottom, I've indicated what it would look like. You see, you're looking at the representation applied to the braid. Say it's S1, S2, inverse S1, and I've written down each braid, and then I multiply it all out. But everything collapses back into just U1, U2, U1, U2, U2, U1, and the identity. So we get that the bracket of the braid is going to be equal to a to the I of b d squared. That's where I is a index, a product of indices of the a's added up. That's just what's coming from the first part of the product. You see, when you take the product, you get AI, A inverse I, and AI multiplied together, and that gives you the coefficient of I. That's separate. You can just assume you know that. That the other part, you have to take the trace, and that comes from this. But we want the trace of something unitary, so we shift it in by a little fiddling to the trace of the entire representation and an extra term. and that trace of the entire representation is now the quantum part. So to turn this into a quantum algorithm for computing the bracket or the Jones, you take the unitary representation phi, you then use the algorithm to get the trace of the unitary phi, and the quantum computer, after running its statistics for a long time, will give you the value of the Jones polynomial after a little extra work. So that's a picture of getting the Jones polynomial by a quantum algorithm. And it is, in fact, the picture of the generalization. We worked this out using that idea of use single projectors. Maybe a year before, a paper appeared, and then we were thinking of generalizing it, but being too slow about that, not seeing exactly how to generalize this either. A paper appeared by von Jones and Dorit Aharonov, which we call the AJL. What's our abbreviation? The AJL algorithm. That's Aharonov Jones. Oh, and there's Landau, right? And their paper uses an idea that goes back into the early work of von Jones on representations of things, and I'm going to describe a bit of it to you. I think I have a better description of the general form of their algorithm on another page. Let me pull that page up. Yeah, I like this paragraph. Oh. Of course, the print is a little fine, and I apologize, but we're going to quit soon. So the AJL representation of the temporally Lie algebra is based on a complex vector space Hn, whose basis is ket I, where I is a 0, 1 bit string of length n. So a bit string, 0, 1, 1, 0, 1, 0, just an arbitrary string of zeros and ones. And each bit string I is seen as corresponding to a walk on a line graph GR with R minus 2 edges and R minus 1 nodes. So for example, here is G5, and a walk on G5 is a walk. So 1, 0, 1, 1, for example, means first you walk from 1 to 2, then you walk back to 1, 0 means go backwards. Then you walk forward to 2, and then you walk forward to 3. And the right end node is 3 in this walk. So a string of n bits is a walk on GR if the walk remains inside of GR for all its steps. And we let HNR denote the subspace of HN spanned by the bit strings that are walks on the GR. And they give a representation of the temporally Lie algebra into a matrices related to HNR. And they're going to do it in a way that, if you look at it carefully, you will see that it actually does generalize what I was telling you. So let me walk you through a bit of this, but you're probably going to want to either look at our paper or the AJL paper to think about the details a little more. So let me give you a reference to their paper. I will, in the Dropbox, I'll include our paper, the slideshow, and their paper. But here is the Aharonov-Jones-Landau paper, still on the archive, but it's long ago published. Polynomial quantum algorithm for Jones. As you see, it was done a while ago. You can find it, no trouble. So here, let's walk through this a little bit. I'm going to let LK, or lambda k, be the sign of k theta. And I'm going to be wanting a unit vector for, a unit complex number for A. They use I e to the I theta over 2. rather than e to the I theta like we did, okay? And then that conveniently makes the loop value equal to 2 cosine theta, and there's no sine there. And then one needs to choose the theta so that the sine of k theta is non-negative, because the same philosophy is being used here. One wants the representation of the temporally Lieb algebra to be real symmetric. So he insists that the sine of k theta is non-zero except for k equal to 0. And then this is a kind of sliding story that you'll see happens in relation to the line graph. Lambda k minus 1 plus lambda k plus 1 divided by lambda k is always d. Well, this is just trigonometry. I want you to do it in your head. I didn't write it down on my slide. But what are we talking about? Sine of k plus 1 theta plus sine of k minus 1 theta divided by sine, what? Is there a question? No. Okay. This guy here is sine of k minus 1 theta plus sine of k plus 1 theta divided by sine of k theta. You use the sine of x plus y equals sine of x cosine y plus cosine x sine y, and turn those each into sine of k theta times something, and add up, and you'll see that it's just equal to 2 cosine theta. Okay? So the representation is going to be given in terms of an EI rather than a UI. EI squared is DUI. They'll satisfy the temporally Lieb relation, and they're going to act non-trivially on the I and I plus first places in the bit string basis for the space. You'll see. And each EI is based upon these lambda i's. And A, an important thing, is the endpoint of the walk described by the bit string that you're using. As I said, the bit strings represent walks on the line graph, and we could do it one more time just for the heck of it. I have 1, 0, 1, 1, and I have this line graph, so I go 1, 0, 1, 1, and end up at 3. I'm sorry. Yes. And yes, I'm sorry, I wasn't watching my indexing. The last one is 3. So you went 1, and you would get 2 if you only did that much. Then the next one, 1, that's where you would land after that, 0, and then 1, and then 1. So 3 and then 2 is the earlier one, z of 4, and so on, z of 2. So you get different z of i's depending on where you truncate. But the main point is you're taking that walk. Now you define a vector, v of a. And that vector is coming out by malice aforethought from the same kind of fiddling that I was showing you for the 2 by 2 case. So I have the square root of lambda a minus 1 over lambda a and the square root of lambda a plus 1 over lambda a transpose. And the EI is the Kepra corresponding to that. So I think I have them here. I'm going to skip to here. To here. There's what the matrices look like. This is one single matrix. All right. And remember that what we were finding was that the lambda plus the lambda minus divided by the lambda 0, whichever one you took, was D. So I have a bunch of matrices. They're a little different as they go along, but each one has square equal to DE. And we're going to put them together to make a representation of the temporally Lieb algebra. Each one is, in fact, a Kepra projector matrix, but they kind of shift one to another and meet one another in the right way in order to give the representation. And that's where I'm going to be vague because we're out of time, and it's a little hard to plug this together quickly. But what then happens is that you take a look at you remember the EI is only going to act in the I and the I plus first places in the string. So I'm taking a sort of general summary of it. That these are set, so they only act in the I and the I plus first places in the string. And you can check what happens when they're neighbors. When they're neighbors, and you look at the way the ket of one interacts with the bra of the next one, you find that you get a one. And so you get invariance under the cup cap from the point of view of the diagram, and that makes sure that the Temperley-Lieb algebra is actually being represented. That's one aspect. And then you have adjusted things so that it's real symmetric and it works. And what about the traces? Well, you define the trace of the representation to be the the sum of coefficients lambda k, the ones I just told you about, times the trace of mk, where mk is the representation restricted to paths that end in k. So that turns out to be the trace that works here. It satisfies the right Markov property and everything, and corresponds to counting the loops. And you can go through a little diagrammatic to show that the trace indeed works correctly, and you get their algorithm. So their algorithm is an interesting um, mixture of using projector matrices and the path structure of the line graph. And they also analyze, and I've forgotten how efficient they were able to make this. It's a little more efficient than it would be if you were doing it in the ordinary classical framework. It's going to look a little more like polynomial time in the quantum sense than the other. And I didn't check my statistics for today, but that's the summary of what their algorithm looks like, and that's where we are.
Oh, thanks,
So,
Lou.
yeah, excuse me. I want to make one more comment. I
Okay.
realize that
Hmm.
this is a good example of something which really requires one to sit down and stare at it on one's own rather than be told about it in a lecture. But I hope that this little guide to their algorithm will make it fairly easy for you to open their paper or our paper and have some fun with it.
Sure. Well, we need pencil and paper, I think, and a good rubber. Oh, eraser, sorry.
Yes, right.
Oh, okay. Well, that's great, Lou. Are there any questions?
So the matrix H, chances are you could have used any matrix as long as it satisfied some condition.
You mean the Hadamard matrix?
Yes.
Um,
So what are you looking for
oh
in that?
well, I could have tried any little 2x2 unitary. It wouldn't necessarily do the job for for the trace for finding the trace of the matrix. And that's a nice experiment, right? Put down an arbitrary 2x2 unitary in there and use the controlled thing, and you'll get a different mixture of things coming in, and you'll compute something about the original unitary.
But like, for instance, would any Cartan involution work?
Would any what?
Cartan involution. So there's a
Cartan?
involution. Yeah.
Oh, a cartan. You're thinking of it as being a square is equal to the identity. Yeah. You could
Yeah.
have used somebody whose square was the identity. It probably will work. Yeah. But you got me curious. I never did that mathematical experiment. If we put in an arbitrary unitary instead of the Hadamard, then we have an algorithm in front of us, right? But what is that algorithm computing? You need to work out the expectation and see what it's computing. So therefore, that's your homework.
Yeah, well, we've got some heavy duty homework to do. So thanks, Lou. And just to say that next week, I think Charlie's talking. Is that correct? Yeah. And I'll send around details about that. Okay. So, yeah, Scott.
Yeah, the cups and the caps by themselves in your last bit are just 1x2 vectors or 2x1 vectors. Is that right?
That's correct. That's what they are in this case.
And is there any relationship between these bit paths and the Dike paths that correspond to temporally lead elements? Are, when we do a zigzag, are we seeing something that's happening with the bit paths, or is that just a strange coincidence?
I haven't made the comparison. It might
Okay.
not just be a strange coincidence. We should look.
Okay, thanks.
Okay, well, I'll stop there. I just want to say something. During the lecture, somebody was trying to enter who just looked like a telephone number. I don't know who that was. I didn't let them in, and and I apologize if it was someone genuine, but I've always, only let in people who I've sent an invitation to, and I certainly haven't sent an invitation to a telephone number. So, but anyway, if telephone number wants to contact me, I'm sure.
I think it was Perko.
Oh, was it?
Oh,
Ah, right. Well, he should have come up as Perko.
The invitation has a phone number link as well to dial in.
He's
as long
made
as I
some.
recognize that, I don't want people barging in and, who are hackers or whatever.
Ken has indicated that, but in the matrix of people, that it was he and everything was okay.
Oh, okay. Right. Okay.
There was a thumbs up there.
That was a thumbs up. Oh, okay. So this person called Susan is not Susan. It's Perko.
Right.
Yeah. Okay. That's fine. So, all right. Okay, guys. Well, and gals, we'll see you all next week.
right. Thank you, Roger.